Hopefully you folks will take some time on your own to look through it. There's definitely some fun stuff here. I'm going to let George make the final closing comments, but I definitely want to make sure that we kind of, the simulation side of it also, because I was talking, what's your name, sir?
James Royster.
We were just talking about to James about the fact that they are experimenting with this idea here at Ames for landing things on Mars without parachutes. How do we change the drag coefficient? How do we change the shape and things like that? And using those type of simulations. So with the simulations, we have the computer simulations taking us from the most basic idea all the way up through the one that Tom made, and then the actual physical simulation, the actual drop test. Does it survive before we actually take that final step of we actually do get to do the complete launch?
Okay. Well, I'd like to thank you very much for your attention. This has been, like I said, a very incredible experience. This is something that we've done as or Kevin has done as a project a couple of times. Now that we've basically gotten a chance to explore it and introduce simulations in a very robust manner, I am very excited about doing this, and I would suggest to you, if any of you are interested in this, you have the website. We are open, just as I think any of you teachers are, to helping you do this project with your kids if you decide to do that. I think we've formed a band of brothers here, and anything you need that we can help you out with regard to this project, we would certainly be glad to help you out. Again, this has been an incredible experience, and I can't tell you how much I've appreciated not only the last 2 weeks, but working with all of you. If you have any questions, we'd be glad to answer them if we haven't already. Thank you.
Okay, question time. Zach, first of all, thank you.
Can you put your names and stuff, the first slide with your names and everything, and the title, please? Appreciate it.
You can't spell Cieszkowski?
No.
Well, I think right there, but
I'm having trouble with Kevin.
There we go.
I got the C part.
That's a start. At a point I was calling it was C and ski.
Hey,
Got the C and I got the ski.
hey, Kevin, do you know why a lot of the Polish type people end in ski?
We're filming.
Because we can't spell toboggan.
That's right.
You can't spell what?
Toboggan.
That wasn't very nice.
Any other questions?
Anybody knew the answer?
One thing that I did run into.
Oh, yes.
Just so everybody knows, one thing that I ran into, I do have the converter on my computer, but it's an older version of Microsoft, so you could run into problems opening up the documents and things.
Oh, okay.
So save your documents in an older version so that
And then open,
yeah,
save them first and then open.
Right.
Okay.
Well, no, but when you guys were
No,
making
when we
your
post them
links,
up.
upload them as an older version of Word or
okay.
PowerPoint, whatever, so that nobody's going to have a
DocX.
problem. Right, exactly.
So some of the other things that might be interesting is try to see if we can model certain things and estimate parameters. For example, if you know the temperature profile, the theoretical temperature profile, and can you use that to estimate altitude, for example? Because the
Tell the material.
So is there some way to figure that out? Things like if you do the wind forecast, the National Weather Service high altitude wind forecast.
There actually is one on here that does that. One of the.
No, just getting the students to do it, not because if the model, the model might do it, but it will not be clear to them
Why it's.
how it is done. So, for example, can they do like back of the envelope calculations and see that if this is the forecast, this is where we expect it to land, and then see if it lands or not.
Right, close to where they. Yeah, absolutely.
Yeah, very good. Again, thank you very much.
Thank you.
Thank you. Again, I know it's kind of hard after 2 weeks of intense work to get up here and try to share this huge amount of knowledge that you've gained as well as the ideas that you have, but I think You did a good job here once again. If you would complete your rubrics and pass them this way so that I can accumulate them, that would be appreciated.
I don't know if you collected from the first one. From the first one?
Oh, yeah, thank you. Thank you.
This is from this one, make sure.
Can I call back now?
Yes. Any others?
Yeah, I got one.
One second.
And acknowledge their presence here.
So if I have to
If
leave
you have
here
that
for a
spot.
Oh,
second.
sure. We want to start out with a message from a special guest.
Good afternoon, ladies and gentlemen. This is Stephen Hawking, and I would like to say hello from the University of Cambridge. I would also like to introduce my very good friends, George Hademenos and Kevin Cieszkowski. Let's hear it for the boys from Texas as they present their lesson, Fly Me to the Moon, or at least orbital space.
That's Steve, he's just a kidder. My name is George Hademenos. I teach physics at Richardson High School. Kevin Cieszkowski teaches at Bergner STEM Academy. We're both physics teachers, and we're both within the Richardson Independent School District. The title, as Stephen so eloquently put, is Fly Me to the Moon, or at least suborbital space. Kevin teaches 9th grade physics under a physics first type of curriculum, and I teach 11th, 12th grade conceptual physics. Our mentor information, again, I would like to extend our deepest gratitude for working with Ernie Fretter. I cannot tell you how much information we learned. The experience was incredibly enjoyable. His research area is Thermal Protection Systems Division. And the major thrust of his research, pun intended, is to look at materials as they re-enter the atmosphere and the effects of heat on them. It's very easy not to consider the enormous amount of heat that these rockets tend to generate as they re-enter the Earth's atmosphere. And so what Ernie's group is charged with doing is testing, coming up with materials that are best suited for these types of extreme environments. So what we are going to do is take that major concept, and we are going to perform a project that we have done in the past where we are going to look at the amount of heat generated within a payload that is subjected to a suborbital balloon flight. The general idea of the lesson is that the students have to design a payload compartment that they will launch in a weather balloon into suborbital space. The objective is for the kids to devise an experiment in which they will determine the temperature variations of the payload compartment as it goes up and then, of course, as it goes down. Now, what they are going to be given are some materials which will be teacher provided. However, they have the choice of selecting from an assortment of sensors. They are free to choose whatever sensors they like, but they are subjected to a constraint from the FAA regulations on a total weight restriction of the payload. This is one of the things that they have to research, they have to look at as they go to design their experiment and arrange it within their payload compartment. Content focus is going to center around two fundamental physics topics. The first one is forces. We know that a force is a push or a pull, and the kids know that when you drop something, the reason it drops is force due to gravity. This works great in an ideal physics land environment. But what they quickly will begin to realize when they are engaged in this project is that air resistance, air friction, becomes an important part of this project. What they're going to have to do is not only understand the forces that are acting on this payload as it goes up, as it comes down, but they're also going to have to extend that concept to realize that the air resistance is going to reach a magnitude in which it cancels out the weight, and then the object becomes non-accelerating, or it has reached terminal velocity. They are going to have to be very familiar with this concept and also how to calculate it. Energy transformations involving heat. One of the major misconceptions of kids at this level is the differences between heat and temperature. Heat and temperature are two distinct entities, but they are related. What they are going to do is devise an experiment in which they calculate temperature changes in the payload compartment, but then also calculate heat using a standard equation. The grades for this particular project are centered around 9 to 12, a high school type of scenario. They are usually either enrolled currently or have had a general physics, and when I say general, I'm talking about a conceptually based physics class, and they at least have the mathematical tools explained in Algebra 1, how to solve, rearrange very simple mathematical equations. But what I would like to mention is that it also is possible to extend this concept into the middle school science departments. We feel that middle school can easily accomplish this type of project and still come away with understanding very fundamental concepts, which we expect our high school students to understand. The learning objectives. At the completion of the lesson, the students will be able to, number one, work collaboratively within a small group to design, to model, to create, to design a payload compartment that will accomplish the objective of the experiment, which is to determine decreases, increases in temperature as it partakes in its suborbital balloon flight. They will understand the effects of air resistance and, more importantly, how air resistance contributes to terminal velocity, and then be able to calculate or at least understand what terminal velocity is and how it applies to the project. Heat is a form of energy, be able to, from their temperature data, be able to calculate the heat generated within that payload compartment. Obviously, design and experiment is one of the key components of this project. We want them to have the freedom to design an experiment which they will have to arrange within their payload compartment to accomplish the objectives of the experiment, but against the constraints of the total weight requirements from the FAA. And another thing they will be required to do is to research GPS tracking devices. This is a great project, but it only works unless you can find the payload once it's landed. So one of the things we place inside the compartment, we actually provide to each student group, is a GPS-enabled cell phone, which, using free software, the kids can easily track at least to some altitude before it loses signal strength, and then be able to identify where it landed, when it landed, and then go retrieve it. This is a small video clip of this project actually done by Kevin's class at the Berkner STEM Academy. Now, please know that the camera on the balloon has recorded about 3.5 hours of video footage. But what we have done is taken small segments just to give you a flavor of what images are being seen by the payload as it goes up, and then at the point where the balloon bursts and starts its descent downward.
And there's going to be kind of a fade to black, and then it'll be at a different altitude because it doesn't show the type of light.
Science aside, this is probably one of the biggest incentives to do this project is for the kids to see what it looks like this high up above the ground.
Roughly how
Very
high?
striking images.
How high up?
I think we counted about 70,000,
I calculated it went
80,000.
to about total about 70,000 or so feet. My guess is this is sitting at about 30,000 at this point.
Yeah.
Yeah.
There's the black sky.
Do you have to get a FAA approval for this or no?
Anything under a certain weight limit, and it's between 4 and 6 pounds, depending on what you use, you don't need FAA clearance. And that's what the students will have to research, so that they know exactly what they can put in the payload.
We're already away from jet routes and things like that.
Pardon? You have, regulations are you have to be a certain distance away. That sound is the strands in the latex are starting to break. So we're actually about to see rapid descent here.
So do you also have position sensors?
And this gets really dizzying, so we don't have a lot of the fall here. To kind of address some of the questions here, first of all, FAA regulations, you need to launch a certain distance away from a major airport. You need to track the weather, where it's coming in from, and we actually have access to a weather balloon tracking device offered by, I believe it's the University of Utah, and there's a number of things like that. And in terms of tracking, depending on how much money you want to put in and things like that, how much weight, you can get extremely sophisticated. We basically bought a $39 disposable cell phone, which was GPS enabled, stuck it in there. Now you lose tracking at about 10,000 feet. So for the majority of the flight, there's no tracking. But once it drops below that ceiling, it picks it up again. And to me, one of the most incredible parts of this activity was we're in a small STEM academy, so they're in one area, had spoken to all the teachers and told them that the kids are going to be tracking this throughout the day. And they disseminated into different classes and things like that. And about 2.5 hours after we launched, there was this roar that went up through all the classes because kids had their laptop turned on, tracking it on a program called Instamapper, and once it was recovered, once it started seeing it again, there was just a big, huge cheer that went up.
Go ahead and hit the next slide. One of the things we've decided to develop as an ancillary component to this project is a website. Websites offered by these sites such as Weebly are not only inexpensive, they're cheap, they're free, which is always a good cost. They're also easy to functionalize, easy to put together. And so what we wanted to do is come up with a website that the students would know to go to get information about the materials, about any handouts, about other websites or sources of information that they could refer to. What I'm going to do is let Kevin launch the website, and I'm going to have him explain the various components. Yeah.
Okay. First of all, our STEM Academy operates on a PBL or project-based learning modality. So our goal is to get these kids working on projects. By the time they're a senior, literally all of their learning is done by projects. So For me, at least, early on, I'm trying to establish with the students certain ground rules and things of that nature, and lots of information is disseminated electronically today. So that's what we're trying to do here. First thing I want to do is definitely, we've got it on here, special thanks to Ernie for all of his work. Also, Tom Benson with NASA Glenn Research actually took an existing simulation that he had and made major changes to it specifically for this project. And we will address that. One thing I don't want to do is go through every single thing that's on here, but I do want to point out certain things. I actually want to give you an opportunity to go to the website and explore, play with some things, see what's on there. Try to make the website extremely simple to navigate. If we go to project information, on here, just a list of different things. And if you can click on introductory letter, this is actually the entry document. For those of you that are familiar with PBL learning, you try and make things as real world as possible and try and emulate a situation. And it usually starts with an entry document. What we have done is we have created an organization called RISD. Well, we are RISD, Richardson Independent School District. Well, for this purpose, RISD stands for Richardson Institute for Space Discovery. And we've created our own little logo here, which is a takeoff on our RISD logo. We placed a flame with the moon. But again, try and really sell to these kids and get them involved in what's going on. Make it interesting and exciting. Basically what they're asking to do is design a proposal for sending a balloon up. It needs to gather as much information as possible. Minimum requirements is it has to have a camera or other recording device so we can see what went on. It needs to have a GPS or other tracking device because, as George said, if you can't track it and get it back, it doesn't do you any good. And it needs to have a temperature probe with a data collection device. We actually have Vernier Lab Quest, which fit well within our weight parameters. You can actually put 2 temperature probes on it, one inside the payload compartment, and you can put another actually outside the payload, so you can actually gather that much data. Now, other things that we put in there, if students want to put an altimeter on it, if they want to put an accelerometer in it, any piece of device with that lab quest, there's lots of different probes, anything that might work as long as it fits in the weight restrictions. The other thing is they need to turn in a proposal. Basically, it's a lab report. This is, for all intents and purposes, a rubric for them. It tells them what they need to include in that report. Now, if we can go back to our main page, or at least to the web page. There's a number of other things on here. I'm not going to go through those right now, other than maybe let's pull up alignment with standards. We actually have 4 pages of alignment with standards, both national and state, not only for science, but for math and technology, because there's a lot of that in this. It's on here. One of the things that we will plan on doing is students will have access to this website, but right now there is stuff on it that is not appropriate for the student. It's not necessary for them. So those can very easily be pulled off when it's introduced to the students. You can create a separate student and teacher website. There are some limits to the number of websites you can create, so I usually only do 1 per project and kind of move things on and off as we go. We do have actual rubrics on there. We have the project write-up rubric. We don't necessarily need to open that. Have a collaboration rubric. For me, that's actually a standard rubric within our academy. What I do want to get to is the simulations, because that's actually what this is all about. Now, there are a number of different simulations that can be run. We have a very basic, in fact, the very first one, if you want to open that up, George, just shows 2 different objects falling without air resistance they fall at the same rate. Click on air reset, click on air resistance, run it. And that's the obvious one. Rocks fall faster because they're heavier. Well, no, they don't. They fall faster because there's air resistance. So we're starting with some very, very simple ones. We also have a wind tunnel simulation on here, similar to the one that Rob and Margaret had. What we want to do with that one, and again, we won't open it, but to show the students, here we're looking for increasing the drag. The eventual goal of this is to be able to launch this without a parachute. And there are some regulations on how fast terminal velocity has to be in order to launch it without a parachute. So you can do a parachute, it costs more money. There are certain issues with that one. It actually is included in the weight in your payload. So if we can eliminate that, and that's the actual goal. If students can design this without having the parachute in there, it's actually to their benefit because they can gather more data. Again, several simulations here. The one that I definitely want to show, and we are going to give you an opportunity to experiment with this and play with it a little bit, is the terminal velocity simulation. This is the one that Tom Benson at Glenn Research helped, actually I wouldn't even say helped create. He created it for us. He was unbelievably helpful. What this allows you to do is change your altitude from 5,000 to basically 100,000 feet. It allows you to change an initial speed, which for us is going to basically be 0. I mean, it's bursting and it's falling freely. Drag coefficient. Students need to do some research on this because depending on the shape, depending on the size, drag coefficient actually changes. It ranges anywhere from 0, basically no drag whatsoever, up to a high level of 4+. But for our purposes, they're going to be between 1 and 2. And by running this simulation, students can see major effect that size will actually have on their, that shape will have on their object. The area in square inches. Obviously, the bigger we can make this, the better. The more surface area to slow us down. We can put weight in there. Again, there are weight restrictions, and this also helps students understand the importance of precision. We don't want to say that's about 280 grams. We want to know it's 277.8 grams because it does make a difference. Every single gram changes it. The beauty of this one also is it gives you a wind speed, a ground wind speed that you can put in there, and when you run the simulation, it will tell you how far away you can project that it's going to land from your spot. The other thing is it gives a theoretical temperature at that height. And that's another thing that we're going to want students to really look at is, theoretically, it's supposed to be -69 or colder at that. Did we actually get to that? What was the temperature outside? What was the temperature inside the payload? If you just want to put in a few things there and run, we're not going to actually run the full simulation because it does take a while. And we can have no wind, so we go straight up. And then you just hit drop. And there's a couple real interesting things that happen here. Because we will talk about, we want to get your terminal velocity down. In fact, we can turn it to metric. I'm a stickler on metric in my class. We want terminal velocity to be between 10 and 15 meters per second. Well, it appears right now we got a major issue. This thing's already up to 158 meters per second. But you notice something happening there. The students are going to have to research, why does that happen? Why does it speed up, and then slow down, slow down, slow down? And there's actually graphs on the left that you can look at and things of that nature. So we'll give you an opportunity, as I say, to kind of look at this one. We'll just kind of leave it running in the background and head back to the the website. There are project websites on here. Project Icarus is a website. Actually, this whole craze with launching balloons started with a couple MIT students about 5 years ago. They called it Project Icarus, and they wanted to see how cheaply they could send up information. Send up a weather balloon to gather information from space, and they did theirs for under, right around $150. We actually did ours for under $100, because usually the most expensive part of it is the helium that you have to buy. And I have a motto: if you don't ask, the answer is no. I went to Party City, which is a local place, that, can we get a helium tank? Here's what we're planning on doing. They said, no problem. I had to put a $100 deposit down on the tank, got that back after it was launched. But really, you're looking at a styrofoam cooler, a couple bucks. You're looking at a disposable cell phone that we got for $39. A camera. We used literally the very inexpensive, probably a $40 camera. Well, not the most expensive, but the thing that made a huge difference is we actually got an 8 gig card, SD card, to put in that so that we could track it for so long. There are other things that you can do where you're literally just taking a picture every 10 seconds or whatever. And one of the students decided, you know what, why don't we just run a full video? And they figured out, you know what, with an 8 gig card in this camera, it'll shoot for 4 hours. That should be more than enough time. So there's a number of websites on here that you can go to. And again, we'll kind of let you folks experiment. You can turn that one down, George. Again, we're not going to necessarily open all of them, but it's information for them. What I do want to do is, and then actually the general websites. Again, a list of some just general information. This is a good picture of basically about the size of the balloon that you're going to get as it launches. Now, if we go back to project information, basically once students have run their computer simulations, now they're going to actually run some drop tests. And what they have to do is an activity where, based on the theoretical final velocity, they have to use some physics formulas and calculate, well, how high is that dropping it from? For example, if it's going 10 meters per second at impact, the final squared equals the initial squared plus 2AD, do some calculations and say that's like just dropping it from 5 meters high. So what they'll do is design their box, put simulated weight in it, take it out to the football field, go up on the stands, figure out that height, and drop it to the ground. And from there determine, is it going to survive? And 2, is that safe? If that were to hit someone, would it be okay? Because the regulations put it between, impact speed needs to be between 5 and 8 meters per second. That's like a, what is that speed-wise? Miles per hour. About 12 miles an hour. That's like if somebody were driving in a car 12 miles an hour and tossed a cooler out at you, just a little small styrofoam cooler, basically empty, is going to cause major damage. This isn't like a rock coming in and hitting a car. So there we have actually a drop test worksheet to help talk them through the calculations. Also, also on here, and this is where we're kind of pulling everything together, it is our thank you letter. What we want to do here is have every student really have some tie-in to this, some buy-in, really feel good about this. Well, we can't launch 120 balloons. Cost is way too prohibitive. We can't even launch one per class, because you figure even if you can get it down to $100, which usually you can beg, borrow, and I won't say steal, but beg and borrow to get that money. And if you have 6 classes, that's $600. So we're trying to keep this very minimal. So what we've done, is that another opening? Oh, yeah. What we've done is come up with a letter at the end. After all the students turn in their proposal, and that's one thing we've done. Even though the students are working collaboratively, individually they need to turn in a report, because this gives them individual practice for writing a lab report. When we have students doing labs throughout the year, yes, they're working together, but they're not turning in just one lab report. Each student needs to do that. So what we basically said in this letter is, we thank you for your proposal. It was an extremely difficult decision to make. In fact, it was so difficult that we couldn't choose just one design. We've come up with a composite design. So the teacher has final say on what's going up and things like that. It also says, your ideas were great. We hope you see some aspects of it in the final design, which we should. There should be certain things in there that a student can say, oh yeah, that's exactly the idea that I had. There should be a lot of that. So there's some real tie-in to this. And then we will pick a spot or a day after school, a Saturday, whatever, where people can go out to the football field or wherever we decide to launch and send it up. One of the beauties of this is George and I, when we landed on the moon, not us personally, but when we landed on the moon in 1969, we were younger kids, that excitement really got us interested in it. And that's what we're trying to do with this. We want the simulation. Those are important. We've got the computer simulations. We actually have the drop test. But we also want them to actually feel what it's like to watch that balloon go up. And you kind of heard that from the students, yelling and screaming and stuff like that. We want them to look back at the pictures that we've got and say, wow, that's amazing. We did that. So this project can be placed at a number of places in the school year. George and I are actually planning on starting our year with this. This will be kicked off within the first couple weeks of school, and depending on setup, you can either run it as about a 2-week intense, that's what you're doing, or over the course of 6 weeks so that you can tie in your kinematics equations and things like that so that the students are learning that as we go along. And let's actually go back to the website, because one of the things that I do is I create this website and students look at it and go, okay, that's kind of cool, and they don't look at the whole thing. So if you actually go to the very last page, this is just kind of one of my...
This one?
No, the general websites. Click on the picture of the balloon. There's nothing that directs them to do this. When they click on this, a file opens that says, congratulations, thanks you for discovering this secret document. You get 10 extra credit points.
Well, it takes a while.
It takes a while, but again, it allows them to, it gives them incentive to kind of explore everything. Oh, when I moved over that picture, it turned into a, okay, there we go. Thanks for taking the time to thoroughly explore the site. And again, gives them some extra credit, and then at the bottom, don't tell anybody else about the link. Let them discover it on their own. We took the time and the effort to create the site, and there's a reason for everything that's on there. So we want the students to explore, to see what is on there. So what I want to do right now is we've got about 5 minutes or so. Is that correct?
15.
Oh, we got 15. Perfect. So if, I know a lot of people have their computers up. If you want to open up, go to this website, take 5 minutes, look at it, what's on there, see the things that are there, play with some of the simulations, and if you can go back to your slide, it shows the website. It's risdballoonlaunch.weebly.com right there. And I say, take 5 minutes or so to just kind of play, explore, see what's on there.